In part 2 of lecture 1, we will discuss transistor basics. There are many different ways of designing electronic logic circuits. The three most significant are TTL, or transistor-transistor logic, MOS, or metal oxide semiconductor logic, or CMOS, or complementary metal oxide semiconductor logic. For a very long time, scientists viewed metals as being conductors and nonmetals as being insulators, with nothing in between. We now know that that is not completely accurate. There's also what are called semiconductors. The key difference between conductors and insulators is the distance between their valence band and their conduction band. Conductors have a valence band that is very close to the conduction band, so it doesn't take very much of a voltage to raise electrons into the conduction band and have electrical current flow. Insulators, on the other hand, have a very wide gap between valence band and conduction band. Therefore, it needs a great deal of voltage for those electrons to be pushed from valence band into conduction band. In electronics, this is also known as dielectric breakdown, but that's a story for a different course. Semiconductors are different in that their gap between the conduction band and the valence band is actually fairly small. While it isn't as close as it is for conductors, it is close enough that with sufficient current, you can easily get those electrons to start flowing through a material. The key to understanding why we are interested in semiconductors lies in understanding what doping is. Doping is adding very controlled amounts of very pure impurities into the semiconductors in question. What this typically means is that we are adding into the semiconductor material impurities that have in their outer shells either fewer electrons than in the semiconductor material or more electrons than in the semiconductor material. The first type, with missing electrons or an excess of electron holes, are called p-type semiconductors. Those with an excess of electrons are called n-type semiconductors. Our use of these in conjunction with each other is something we'll talk about in about a minute or less. We can form junctions by placing doped semiconductor material next to other doped semiconductor materials. This works if they are different type, P next to N or N next to P. Diodes, which allow current to flow in one direction, have a PN junction, whereas bipolar junction transistors have a PNP or NPN junction, and this will allow us to use them to make electronic switches. This allowed them to replace vacuum tubes, and before that, electrical relays. The most successful family of bipolar logic circuit designs is transistor-transistor logic, where we take bipolar logic circuits that have junctions where positively doped semiconductor material meets negatively doped semiconductor material. This was first introduced in the 1960s and very quickly replaced vacuum tubes. Transistor-transistor logic is now a family of logic families that are compatible with each other but differ in speed, power consumption, and cost. This has largely been replaced by CMOS logic in the 1990s. MOS is an abbreviation for metal oxide semiconductor, where we can increase the voltage, and this will decrease the effective resistance of the transistor. It wasn't used until the 1960s. That fabrication method made it practical to use these in manufacturing. While MOS circuits are significantly slower than transistor logic. They used much less power. CMOS, or complementary metal oxide semiconductor logic, is an improved variation on MOS logic and is commonly used in large-scale integrated circuits. CMOS logic is the most capable and easiest to understand commercial digital logic technology. Originally, because of its low power uses, it was used primarily in battery-powered electronics. However, these days it's used in most electronic equipment.